All right, so this begs the question, why does this product rule work? Why is it this? Okay, I'm going to give a sort of an informal proof of this, similar to the one that's in the textbook. This is a really classic kind of explanation for the product rule, and it kind of relies on some geometry. So first of all, we are creating a function by multiplying two other functions together. There's a situation in geometry when you do that, which is finding the area of a rectangle. So let's kind of represent this function f times g as the area of a rectangle. And then f and g individually would be the width and length of that rectangle, right? So that's what I've got depicted here. It's my rectangle, got my f, got my g. So then let's say that fg is something which is growing, right? What we're trying to do is find the rate of change in the area of this rectangle. So that implies that the width and the length must be changing somehow, right? So over here, we're going to change this by some amount. We'll call it delta f. And over here, let's say we change this by some amount. We'll call that delta g. So these are technically f and g are both dependent on x. And so these are the resulting changes in f and g that occur, that are produced by some specified change in x. But the change in x is not really part of this picture right now. It's a little hard to wrap your head around, but yeah. So anyway, we've got the change in f and the change in g. So now the change in f times g is going to be the amount of area that's added on to this rectangle. So I'm going to kind of highlight it in this red here. That sort of L-shaped piece right there, that is the change in fg. All right, all of that. So the question is, what is that? How much can we calculate that amount, that area? Well, yes, we can. Let's break it into three pieces, like this. This piece right here has a length and width multiplied together. It's going to give us delta f times g, right? Because that's delta f, and then this length g is the same length as that piece there. And then for this one over here, you've got width f and then length delta g. So there's your f times delta g, right? But then you have this little piece up here, which is delta f times delta g. So this delta fg is all three of these pieces added together. Delta f times g plus f times delta g plus delta f times delta g, like that. So now, what if we want to do the derivative of fg? All right, time to do it. The derivative of fg, like any other derivative of function, is the limit as delta x approaches 0 of the change in the outputs, delta fg, divided by the change in the input, delta g. So in other cases, you could write like delta y divided by delta g, but then we usually calculate delta y by doing a difference in function values, right? Like the f of x plus delta x minus f of x. However, in this situation, instead of calculating delta fg by that change in function values, let's calculate it the way we did with, just calculating area in our little picture. The numerator here, the change in the output, is going to be that. So that's delta f times g plus f times delta g plus delta f times delta g, delta g, all over delta x. In fact, let's distribute that division by delta x. Like that. So each individual term now is divided by delta x. And now we can do this thing where, remember, if you have part of your expression in here which is not actually dependent on delta x, then you can factor it out, right? So like, for example, the g from this one is not dependent on delta x, so we could factor it out. And the f here is not dependent, so we could factor it out. So we're going to have splitting up the limit and doing that kind of factoring out. I'd say factoring, but I shouldn't call it factoring. It's more like just kind of like using that constant multiple rule. It's g times the limit of pulling out the g, you would have the delta f over delta x, and then plus. For the second term, we'll pull the f out and have f times the limit, and then what's left over in there will be the delta g over delta x. And then for this third piece, we can kind of split that up as, let's take that, delta f over delta x, and do the limit of that. And then let's apply that product rule for limits, where we'll say the limit of the product, this is g here, is the product of the limits, like that. All right, so now what do we have? By definition, that chunk right there is f prime. That's the derivative of f. So here's our g times f prime. This part is the derivative of g. That's just g times, or f times g prime. And then over here, we have the derivative of f again, f prime, but this part right here, since delta g, since g is a function which depends on x, if you have the change in x approaching 0, as long as your g function is a continuous, smooth function, then you can be guaranteed that a 0 change in x is going to produce a 0 change in y. In other words, like this delta g is also going to be approaching 0 as delta x approaches 0. So that's times 0. And that's the part that makes this kind of informal. I'm waving my hands around that. There's some conditions under which this applies. But basically that part is becoming 0. So this term disappears, and we just have the g times f prime plus f times g prime.